Over the last 5 months, I've been testing the loads that I developed in phase 2 of my Developing a Magic Grade Load series. I've tried over 200 loads, I've fired over 2,200 rounds, and admittedly that's a lot. That's quite a bit more than you really need to use in order to come up with an acceptable load, but it's my hobby. I enjoy doing it, so I tend to go a little overboard. So this is way more than you really need to do. Now, I've used cases from 5 different manufacturers. I've used 12 different powders, and I've tried out 10 different match grade bullets. And all of that testing resulted in 7 acceptable loads. Using cases from 2 different manufacturers, 3 different powders, 2 different bullets. One of the things I've noticed, my rifle doesn't seem to like bullets over 168 grains. I've tried identical bullets at 178 grains. I get horrible results. So something interesting I noticed about my rifle is 168 grains seems to be the highest weight my rifle likes. And I found that 3 different powder weights that work well with those 7 loads. Now, what's an acceptable load? Well, it kind of depends on the shooter's skill level. Um, Most people base their tests on group sizes, the smallest group size, smaller group size being better. I use a threshold of 1 to 2 minutes of angle. Now, a minute of angle, 1 minute of angle is 1 inch at 100 yards. It's actually 1.047 inches, but that's close enough. Most people just go by 1 inch at 100 yards, 2 inches at 200 yards, 3 inches at 300, and so on. Now, I always shoot 2 5-round groups and use the best group size that I get from those 2 5-round groups. Now, if I can shoot sub MOA or 1 to 2 minute of angle groups, then I repeat it a few times to verify it. Once I've determined that at 100 yards I can shoot sub MOA groups, then I'll run it out to 200 yards and shoot the same load at 200 yards. See if I can do the same there. Then I'll run it out to 300 yards, etc. So I should always start at 100 yards. If I get good results at 100, I move out a little bit from there. In order to remove some of the human factor out of it, I always use my Caldwell lead sled, and I have the Magneto Speed V3 bayonet style chronograph that I use, and that takes a lot of the human error part out of it by mounting it in the lead sled. Now I also use a target camera so I can get immediate results. You see it there on the right. The computer is connected to the target camera that's sitting out there by the target. That way I can measure group sizes and things like that while I'm shooting, and I don't have to wait for the range to go cold and then go out and do my measurements and things like that. I can see it in real time as we shoot. Now my son Cody does most of the shooting. He's the family marksman. I've been shooting since I was 11 years old, but he picks up a gun, and in 2 years he could be a Marine sniper. So irritates me no end, but that's neither here nor there. Now, how do we tighten up these groups? We've got some loads that work pretty well, but we want to get them a little tighter, as accurate as possible, as consistent as possible. Well, to figure that out, let's take a look at a ballistics calculator and see what kinds of things affect the trajectory of our bullets. Now, this is the Reloaders Workshop ballistics calculator, and we have several input parameters over here on the left. The workshop database we can ignore. All that does is help us fill out the other parameters. Under input parameters, we have the bullet information, the ballistic coefficient, the bullet diameter, the bullet weight, and the bullet length. The next line down is the zero range and the sight height, which really doesn't have an effect on you. We can't do anything as a reloader that'll make those useful. Now, atmospheric conditions, of course, do affect the trajectory of our bullets, but we really don't have a lot of control over that unless you've got connections that I don't have. Uh, and basically from shot to shot, the atmospheric conditions will remain relatively the same, with the exception of maybe wind direction. But the temperature, the altitude, barometric pressure aren't going to change that much from shot to shot. So there's really nothing we can do about it anyway. So we can ignore the atmospheric conditions from a reloader's point of view as far as getting more consistent trajectories out of our bullet. And the output options really are for displaying these charts down here at the bottom and for our trajectory table over here on the right. So they don't have anything to do with the trajectory. Over here we have the muzzle velocity, and that obviously does have a significant impact on the bullet's trajectory. So what we're basically looking at is this first line of input parameters that describe the bullet itself, and over here the muzzle velocity. Now if we look at our trajectory table, the second column here is the drop in inches at various ranges. Now if we look at this last range here, we have 500 yards. The bullet in this particular scenario is going to drop 78.4 inches. That's with a bullet with a ballistic coefficient of 338.338 and a muzzle velocity of 2,400 feet per second. Now, watch what happens to this number right here if I just change the muzzle velocity by 20 feet per second. We start out at 78.4. If I add another 20 feet per second, the drop goes down to 76.84. Now that's a little over 1.5 inches difference in the impact point of our bullet with just a 20 foot per second difference in muzzle velocity. So obviously the muzzle velocity has a significant effect on our bullet's trajectory. So one of the things we can do as a reloader is try to get our muzzle velocity as consistent as possible from shot to shot within a particular batch of bullets. Okay, let me go back to 2,400 feet per second. Now, other things that affect our trajectory, you might expect the bullet weight to affect this table here. Okay, for instance, we have a bullet weight of 168 grains here. If I change that to say 150, you'll see it has absolutely no effect on the drop. It's still 78.40 inches. So simply changing the bullet weight doesn't do anything to our ballistic table. The reason for that is you would think that a heavier bullet would drop quicker and so on. The reason for that is the bullet weight and the bullet diameter are used to define the sectional density of a bullet. Now you can check out my video on sectional density and ballistic coefficient for more information about exactly how that works and what the formula is for determining the sectional density of a bullet. The ballistic coefficient already takes the sectional density into account. So the bullet weight and the bullet diameter are already figured into the ballistic coefficient. The ballistic coefficient is actually a ratio of the sectional density to the coefficient of form, or the shape of the bullet, whether it's a flat point, round nose, spire point, etc. All of that's taken into consideration when they determine what the ballistic coefficient of a particular bullet is. So simply changing the bullet diameter or the bullet weight, or even the bullet length for that matter, will not affect the trajectory of the bullet. The only thing that will change it, of course, are the muzzle velocity, as I've shown, and the ballistic coefficient, since the ballistic coefficient takes the weight and the diameter into account. Now, with this particular bullet, we have a ballistic coefficient of 0.338. Now, that gives us a drop of 78.40 inches. Now, if I change that to 0.330, look what happens. It drops 79.81 inches. Okay, with 338, it's 78.4. 330, it jumps up almost 1.5 inches. So we get even more bullet drop or an inch and a half extra bullet drop simply by having a very minor change in the ballistic coefficient. Now, since the bullet weight is used in determining the ballistic coefficient of a bullet, changing the weight will change the ballistic coefficient. So on this particular table here, if I change the weight, say, to 150, typically a bullet with a lower sectional density or a lower weight to diameter will lower the ballistic coefficient. So say go down to 0.3 ballistic coefficient. You'll see here that it has a significant change. Here we're at 86.21 drop. So simply changing the bullet weight will change the ballistic coefficient, but it's kind of hard to tell without, extensive testing what a bullet that weighs maybe 3/10 of a grain more than another bullet, how much that would affect the ballistic coefficient. So our best bet is to make sure that each of the bullets that we have are exactly the same weight. That way they all have the same ballistic coefficient and they won't affect our bullet drop from shot to shot. Okay, so there's two things that affect our trajectory table: the ballistic coefficient and the muzzle velocity. Both of those have a major impact on the trajectory of our bullet. So, given that those factors are what we're trying to make more consistent or modify in some way, let's take a look at what we can work with here. Basically, we've got our four components. We've got our powder, our primers, our cases, and the bullets. So how can we use these differently or more precisely in order to make our cartridges more consistent? Well, if we take the powder, obviously different amounts of powder, different kinds of powder, different manufacturers and so on are some of the things that we can do to affect muzzle velocity. But we've already pretty much done that quite a bit in phase 2, and be honest, we'll continue to be doing that as time goes on. Once I've found a good load, I'm not going to stop there. I'm going to continue to test. Now we're already measuring our powders out down to 1/10 of a grain. There's not a whole lot I can change about this. I can't modify the powder. I can't measure it somehow differently than just getting it as accurate as I can from cartridge to cartridge. So the powder's not going to help me out here. Next component I have is a primer. Now, measuring the primer doesn't do much good. There's really not that much variation in the dimensions of a primer. There are some qualities of a primer that I can test, but we're not going to do that until phase 2 or phase 3 part 2. So let's leave the primer alone for right now. It's a very minor player in the whole scheme of things, but there are some things we can do with it. Now, so we're left with our cases and our bullets. Well, one of the big factors in the ballistics table regarding the bullet is, of course, the bullet weight and the ballistic coefficient of the bullet. Those two factor in quite a bit in our ballistics tables. So that's something that we can work with. We can tighten our groups up by maybe working with those two aspects of our bullet, weight and ballistic coefficient. Now our cases, what more can we do to the cases? I mean, we've measured them, we've trimmed them, we've set our head spacing, we've done quite a few things with the cases. One thing we haven't done with them is weigh them. Now, the case weight is not something that's factored in on the ballistics tables. So what is the point of weighing the cases? Well, we'll talk about that in just a little bit, but that's another dimension of the cases that we can use in order to try to tighten up our groups. And we'll talk about that in just a second. So, muzzle velocity is one of the major factors that affects the trajectory of my bullet. Now, how can the case affect the muzzle velocity? Well, take for example if I have an air tank. It holds a volume of 1 liter of gas, or the internal area inside there will hold 1 liter. Now, if I were to pump compressed air into this tank until I have 20 psi of compressed air in there, and then I were to open the valve on the top of the tank there, that air would come shooting out the top. Okay. Now, let's say I also have a 5 liter air tank, exactly the same kind, but this one holds 5 liters of the internal volume there will hold 5 liters of gas. If I were to take the gas that's in my 1 liter tank and transfer it over to my 5 liter tank, since I have exactly the same amount of gas that I used to have in my 1 liter tank, but it's now in my 5 liter tank, it has a much greater volume to fill. So I may only get 4 psi of pressure inside that tank. Now if I were to release or open the valve at the top of the tank, the gas would come out, but it would come out at a much slower rate. Okay, because I have much less, 5 times less pressure in the larger tank. Now, you can think of your cartridge case as a small little air tank, okay? It has an area inside that can hold an amount of gas, amount of the internal volume of the case can hold just so much. Now, when I pull the trigger and I light up the powder that's in that case, it's going to start generating gas. And that gas is going to expand until it fills up the case and starts generating pressure on the inside of that case until the pressure becomes so much that the bullet pops out of the end of the case and shoots down the barrel. Okay. Now, what I have essentially then is the combination of the interior of my case and the bore of my barrel can hold only so much gas. And given with a given amount of gas, it's going to generate a certain amount of pressure. That pressure is going to propel the bullet down the barrel at a particular velocity. Okay. Now, what happens if the walls of my case are much thinner? Well, with thinner walls on my case, I have a slightly larger volume inside that case to hold that gas. So when I pull the trigger, light up that powder, and the gas starts expanding, it has a larger area inside that case to fill. So it's going to generate pressure, but it's going to be a little bit less pressure than the case that had the thicker walls. It's still going to pop the bullet out of the top of the case and propel it down the barrel, but it's going to do it slower because I have less pressure now because I have more volume that gas has to fill. So the challenge becomes, how do I determine, say between these two cases, these are 308 Winchester cases, how do I determine if the volume inside this case is the same as the volume inside this case? Well, you might think maybe you could measure the case wall at the neck here and do the math and figure out if they're about the same. The problem with that, of course, is there's manufacturing variances. The parts of the case wall may be a little different in one area than another, so it kind of throws off your calculation. Fired brass would maybe stretched a little bit in one area and have a thinner wall in one spot than it does in another. So you can't really do it mathematically. Now, one school of thought is that if I weigh the two cases, that the case with the thicker walls will weigh more than the case with thinner walls. Since it has more metal to it, it would weigh a little bit more and would therefore have a little, the thicker wall case would have a little less volume inside, generate higher pressures and therefore higher muzzle velocity than the case with the thinner wall. Now I can, easily enough, weigh my cases. See, this one is 164.9 grains, and this one is
165.7. So there's a difference of 0.8 grains between the two cases. So one case being a little heavier probably has thicker walls. And for most reloaders, that's close enough. That's the way they do it. And I've done it that way myself, and I've had good results. The problem with doing it that way is that the difference in weight may be down here in the head. Maybe there's a little more material on the head of this one than there is in the head of this one, and that may be the difference in weight. And even though the volume of these two cases might be identical, I'm getting different weights because of the head weight. Also, you need to make sure that your cases are deprimed before you weigh them. Otherwise, the difference in weight may be the weight of the primer. You also want to make sure that they're cleaned. If it's brand new brass, you've got no problem. But if it's fired brass, you would want to size it, headspace it, trim it, do everything you're going to do to that case before you weigh it, especially the trimming, because if you're taking material off the case, that's going to change the weight. So you want to make sure you trim them before you weigh them. But you also want to make sure they've been cleaned thoroughly. If one has a little extra dirt or debris inside than the other one, that may change the weight as well. So you would, since the inside of the vibratory tumbler doesn't really clean the inside of the case, you'd probably want to use a wet tumbler to clean the brass before you weigh it. Now, as I said, the difference in weight may be in the head, and that, of course, will skew your results, and you may or may not be getting two cases that, they may weigh the same amount, but one of them may have thinner walls than the other, and you'll get a different volume, therefore different muzzle velocity because of that variance in the head weight. So, how do we resolve that? Well, that's where the H2O method of weighing cases comes in. Now, with the H2O method, the idea is that we fill the case up with water, and then we determine what that water weighs. And the idea here is that a given volume of water will weigh the same as another given volume of water that's identical. So if a case holds more water than another case, then it'll weigh a little bit more when it's full of water. We can assume then that the volume of space inside that case is smaller, and it'll generate a higher pressure. So what we want to do then is separate our cases so that all the cases in our batch of ammunition that we create hold exactly the same amount of water, and we determine that by filling the case with water and weighing the water. Okay. Now to do this, of course, you'll need a supply of water. You need a place to put the used water. You'll need a syringe or some way to put water in the case. Now I use these epoxy syringes. You can get them at just about any hobby shop or Amazon or whatever. They only cost a few bucks, but they're made for mixing epoxy, but they hold water just fine. Now, since the cases need to be deprimed, we can't really fill them with water because the water will come out the flash hole, and it won't do us any good. Well, 21st Century has these primer pocket plugs. They're about 10 or 12 bucks a piece. They got one for small primers and one for large primers. And what you can do then is put the primer plug into the primer pocket. Get it all the way in there. Okay. And now we have a case that we can fill with water. Now what we're going to do first is weigh the case without water. So we'll put that on the scale. And we get 444.8. That's the case by itself. Then what we'll do is we'll fill the case with water. Now a couple things about this. Number one, the reason we deprime them is that since the water will go through the flash hole and into the primer, the volume inside the primer may be different from case to case. Of course, if you have a brand new primer in there, you're ruining your primer. But if you have a fired case that has a used primer in it, the volume of that primer, that used primer may be different than the volume of the next case's primer. So make sure you deprime them. We also have an issue with any debris that's inside there will not allow us to get as much water in as we would with a clean case, so it has to be cleaned. We also may get air bubbles. So once we put the water in there, we need to tap it a little bit to get the air bubbles out of there. And the biggest problem is water tension. Now when I fill this, I'm going to fill it nice and slow. If I shoot it in there real fast, it'll be more apt to bubble up on me. So I'm just going to put it in there slowly until I get right about the top there. Now you see the surface tension kind of has a convex top to it there. Now I need to make sure that I fill all my cases the same way. Maybe on one, if I have one that's a little concave and the water tension has it going down a little bit in the middle, and then the next case I have it convex where it comes up a little bit, that means I'm putting a different amount of water in each case. So you need to make sure that you fill the case the same level so you have the same kind of top or water tension on the top of your cases. I'm also going to flick the case just a little bit and make sure I have any bubbles that may have formed inside the case out of there. Okay? And make sure there's no water on the outside of the case, because that's just going to skew my results. And I take the case and weigh it with the water in it. And here I get 499.8. Okay? So, the water weight, the difference in weight between the case by itself and the case with the water in it is 5 grains. 55 grains. So this case holds exactly 55 grains of water. Okay, gotta take the plug off of it to get the water to come out of the case. Now, of course, one of the downsides of using the H2O method is now I have a case that's wet on the inside. If I were to put powder in there, this would basically become a misfire. So when I do this, I have to take all the cases that I've done this way or use the H2O method to weigh them, and I have to dry them out. I'll usually put them in my brass dryer and dry them out the same way I would as if I had wet tumbled them. So the H2O method involves a little more work, obviously, than just simply weighing the cases, but if done right, you get a much more accurate weight or a much more accurate measurement of the volume inside the case based on water weight. So with this one, the case by itself is 444.1. Okay, and I'll take this case and fill it with water. See how water tension will bubble up like that into a convex shape here? I don't know if you can see that. Let me zoom in on that a little bit. Look at that. That water is sitting way up high. Okay, and that's going to give me a false reading because the other case that I did was relatively straight across. So what I want to do is take that down a little bit until it's about the same shape on top as the other case that I did, and that's right about there. Okay, I'm going to flick it a little, get any air bubbles that might be in there out of there. If you've ever seen the doctor, before he gives you a shot, he'll do that to the syringe to get air bubbles out of the syringe. I'm just going to do the same thing with the case. Make sure there's no water on the outside, and carefully place that on the scale. and I get 499.6. So this particular case holds 55.5 grains of water. So there's a difference of 5 grains of water, which means that this case, since it holds more water, the interior of this case has a slightly higher volume than this case. So the case walls may be a little bit thinner, or the manufacturer's variances in the case thickness equal a little less total wall size than this one does. So it's a 0.5 difference. Now you need to make kind of a decision on what constitutes an acceptable difference in water weight. 0.5 is not that much, but the reloaders that I know anyway typically use about a 0.2 to 0.3 grain difference as being acceptable. So what I would do here is I would put these two in separate piles. I would mark the weight of each pile, and then I would go through all of my cases and group the cases that all have the same water weight and therefore the same volume, interior volume, and until I get an idea of how much difference there is from case to case. I may get a group of cases that all weigh exactly the same, and I'll take that group and put them in a box, and that'll become a little family of cases that all have exactly the same interior volume. I'll load those up and check the muzzle velocities from shot to shot, and what I should end up with all the cases having the same interior volume, therefore generating the same amount of pressure, I should end up with a more consistent muzzle velocity and therefore more consistent group sizes. So that's really all there is to the H2O method of weighing cases. Now, that brings us to the bullets. Now, as we saw in the ballistics calculator, the ballistic coefficient was one of the major components or factors in determining the trajectory of my bullet. And the weight, of course, is figured into the ballistic coefficient of a bullet. So if I have bullets that weigh a different amount, then they're going to have a different ballistic coefficient. So I can use my scale here and simply measure the bullets and make sure they're all the same weight. And what I normally do is I'll take a batch of bullets and I'll group them up by weight, all the bullets that weigh the same, and then I'll take a batch of bullets that all weigh the same and use those in a batch, or actually go through another test. So here I have, this bullet is 150.2 grains. This one is 149.9. So these two bullets are actually 0.3 grains difference in weight. So I would group these slightly differently and go through the rest of the batch and group up all the bullets that weigh the same into groups. Then what I do is, in addition to the weight affecting the ballistic coefficient, from batch to batch, the manufacturer may have created bullets that have a slightly different ogive. Now these are not match grade bullets. These are just 150 grain regular bullets, spire point bullets with a soft point on them. So I wouldn't use these in a match environment, but I'm using these for demonstration purposes only. Now, one thing I can do, this is my Hornady bullet comparator. And what it does normally is I measure the CBTO of a cartridge. In other words, from the case base to the ogive of the bullet. CBTO, case base to ogive. What I can also use this for is to measure the bullet by itself without being in a cartridge. So I put the tip of the bullet in the appropriate sized adapter for 308. And I see that this bullet is 0.581 thousandths, or 581 thousandths. And I do the same thing with this bullet, and I find this one is 583.5. So these bullets, the base of the bullet to the same point on the ogive of each bullet is off by about 2 thousandths of an inch. So I can further then separate this batch of bullets that all weigh the same into bullets that have a slightly different ogive. Now, typically with match grade bullets, there'll be very little difference from bullet to bullet, but if in case you accidentally mix lots of bullets, you got about 3 or 4 boxes of bullets, you put them all together and they came from a different lot number from the manufacturer, they may be a little bit different, but bullets like this, these are just inexpensive 150 grain bullets. I expect them to be a little bit off. Now, another measurement you can take. Now remember, the measurement we just took here was from the base to a point on the ogive of the bullet. Now let's look at another way to measure these bullets to make sure they have the same ballistic coefficient. Now this is my Reading instant indicator. Now you can check out my video on the Reading instant indicator for more information about all the different things that this does and how it works. But essentially, what this will do is measure the difference between bullets. It's a comparator. It's not a measurement device. It'll compare the difference between the base of the bullet to the point on the ogive where it will meet the lands and grooves of the lands of the bore. Okay. Remember, my bullet comparator, the Hornady bullet comparator, measured it from the base to a point on the ogive. This is going to measure it from the base to the point where the bullet will actually meet the lands in my bore. And I set it up to do that as a bullet comparator. I'm going to put the bullet in the case here that comes with the Reading indicator upside down, and I'll run that to the top and I'll zero my scale. Okay, so now it's zeroed on this particular bullet. Just test that out. Okay, so it's zeroed. Now I'll take that bullet out and I'll put in the second bullet, and I see this one is off by 7 thousandths of an inch. Now that's quite a bit. So the distance between the base of the bullet and where it meets the lands is 7 thousandths of an inch different than this bullet. So I may group these two bullets a little bit differently. Okay. Now, doing these kind of measurements does a couple of things for me. One, if I measure from the base to the ogive, and I then use the base of the case to the ogive to seat my bullet, if there's a difference in the ogive, one bullet may get seated a little bit deeper in the case than another bullet. And what that's going to do is, if it's seated deeper, that means there's less volume inside the case for the gas to expand, which means the initial pressure that builds up is going to be a little bit higher. And that's going to result in a higher muzzle velocity if it's seated a little bit differently. And the weight of the bullet, of course, being a little bit different. If I have a different measurement from the base to the ogive, that means the shape of the bullet is slightly different, and that's going to mean a different ballistic coefficient. The weight of the bullet also being different is going to mean a different ballistic coefficient. And as you saw when we looked at the ballistic calculator, a small difference in ballistic coefficient can mean quite a bit different impact point on my target. You saw that 0.008 difference in ballistic coefficient came out to an inch and a half at 500 yards. So these kinds of measurements will make sure that all my bullets are identical, both in the shape to the ogive and in where they meet the lands of the rifle, and the weight, to make sure that the ballistic coefficient is exactly the same from bullet to bullet, so I get consistent points of impact. Okay, so I've used my cases using the H2O method to try to get more consistent muzzle velocity from my cases. I've used my bullets to try to get a more consistent ballistic coefficient. and muzzle velocity to make my reloaded ammo more consistent from shot to shot. So what I'll do then is I'll take those 7 loads that I created. I'll apply all of these techniques that we just did. I just showed you in this video to the bullets in the cases, and we'll run tests on those 7 loads. Now, why didn't I do that to begin with in phase 2? Why didn't I use the H2O method to weigh the cases or find the volume of the cases in phase 2 before I even started? Well, or same thing with the bullets. Why didn't I do this with the bullets? Well, what I wanted to do really was find out which manufacturers, which bullets, which cases already had fairly consistent results. Very similar muzzle velocities. I usually take a look at the standard deviation in muzzle velocities from group to group, or from round to round, cartridge to cartridge, to determine if one manufacturer's cases give me wildly different muzzle velocities, whereas another manufacturer gives me very similar. Now I found that Lapua, Norma, and Hornady cases are fairly consistent, while some of my reloaded Winchester cases, my Remington cases, gave me much bigger differences in muzzle velocity. So I can kind of figure that the volume of Remington cases, for example, is much more varied from case to case than, say, a Lapua case. So I want to find what cases come from the manufacturer already consistent, so that when I actually do the H2O method or weighing cases, or I use my measure my bullets using the bullet comparator or the reading instant indicator, I've already got something that's fairly consistent to begin with, and I have very minor changes. Otherwise, I end up with huge disparity between cases, and I may not get enough cases to put together that all weigh the same, for example. So that's phase 3, part 1 in my developing a match grade load series, trying to tighten up those groups that we came up with in phase 2.
That's all for this video. I hope you liked it. If so, please click the like button. Maybe even subscribe to my channel. Thanks for watching, and happy reloading.